open the Fluent software, and as this is 2D problem, we will select 2D from here and double precision. Okay, so double precision means the number of decimal places will be more in calculation rather than in single precision. And there is another option of using serial processor or parallel processors. So if you select parallel processor, so we can use number of cores in 1, 2, 4, 8. So because this laptop have 4 processors, so we will use 2 processors, okay, for calculations. And this is the working directory. Working directory means where the Fluent files will be saved. And click OK. Once the Fluent file is open, the first of all we will read mesh. So we will discard case and read new mesh because we are starting afresh. So we will read mesh file. So read mesh, discard cases and read new mesh. So this is our mesh for the cylinder. So the software is reading your mesh. So once the mesh has been read by software, go to the display and click display. So in your display tab, your mesh will be displayed. Okay, so you can zoom and you can see your array of cylinders. So there are 16 cylinders in a squared arrangement, and every cylinder has geometry diameter 1, and they are placed apart at a 2.5 diameter. And let us check the mesh size. So the mesh size is 2,2459, and check mesh. The check mesh will give volume statistics. The minimum volume is of the cell is this much, and this should not be negative. And the domain extent. So the domain extent is -40 to +40 in the x and y direction. So we have 80 by 80 domain, and at the center of which this array is placed. Okay. You can also check the quality of mesh. This tells about the quality of mesh, and which is 0.5376, and which is a good quality. And now we will tell you that this is the domain, and this is inlet boundary, this is outlet boundary, and this is symmetry. The top and the bottom surface are symmetry. Now we will set up the physics for the problem. Now go to the general, and this tab will be displayed. Select pressure based for incompressible flow, and if the flow is dense compressible, then select the type density based. Because our problem is incompressible flow, fluid flow over an array of cylinder at Reynolds 100, so we will select pressure based solver. And if the fluid flow is unsteady in nature, then select transient. Now move to the models. So in models, you can select the appropriate model for your simulation, because the fluid flow here is viscous laminar at Reynolds number 100. So we will select the laminar model. If the fluid flow is turbulent, you can select any of the turbulent model to solve the turbulent flow for different turbulent regime. And if there is involvement of temperature, then you can turn on the energy equation. But in our problem, this is the fluid flow without heat transfer, so we will not check this option. And now expand the material panel, and the properties are, we will put density 1, viscosity 0.01. Why? To achieve the Reynolds number 100, because the Reynolds number is rho v L upon mu. Rho is selected 1 V is the velocity, inlet velocity. We will provide the value of inlet velocity as 1, and L is the characteristic length. Here is the diameter of the cylinder, which is also 1. So rho V and L are 1. So by changing the mu, we can obtain different Reynolds number. So if we want to do simulation at Reynolds number 100, we will select viscosity value 0.01. Now click on change and close this box. Next is cell zone condition. There is only one cell zone, that is fluid, and everywhere fluid is considered. There is nothing solid material. And then we will go to the boundary condition. So at the bottom, the boundary condition is set to the symmetry, and at the top also the bottom is symmetry, and C1, C10, all these are the cylinder number. Let me show you. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, and 16, and so on. So there are 16 cylinders numbered from left to right. So all these cylinders will have type of the boundary condition as wall. Now select inlet, edit. The type of the boundary condition at the inlet. The inlet is our leftmost boundary, this one. And the type of the boundary condition will be velocity inlet, and the value of the velocity we will set 1 meter per second normal to the boundary. Okay. In the interior we don't have to do anything and leave it at its default value. At the outlet, the boundary condition will be set as pressure outlet, means the fluid flow is exiting at atmospheric pressure, so the gauge pressure will be 0. So leave other things as it is at default value, press OK. The top boundary condition we have already set. Now the boundary condition part is OK. There is no dynamic mesh. The mesh are not moving. Select the reference values from inlet. These reference values will be used to calculate drag and lift coefficient. Now in the solution methods, we will select scheme to solve the Navier-Stokes equation. There are 4 schemes, 4 strategies to solve Navier-Stokes equation for incompressible flow, and the simple is semi-implicit pressure correction based method, and the discretization of pressure terms we will select second order, and momentum we will select second order, and in case of transient formulation we will select bounded second order implicit, which gives more accurate results in unsteady flow. Now leave the control sections. These are the parameters which controls the solution's convergence. Usually we leave it at default value, but if the solution is not converging, we can reduce these values according to the problem. Now next, go to report definition. In new, we want to plot drag at cylinder number. Let me show you. So this is 5, 6, 7, 8, 9, 10, 11. So we will plot the drag value at the inner core of the cylinder, which are surrounded by other cylinders in all directions. So this is 6, 7, and 11, 12. So at 6, 7, and 11, 12, we will 6, 7, 11, 12. We will plot the drag, and the drag direction is in the y-x direction. Create file, report plot. Report file means a file will be generated, a notepad file, text file that can be opened in notepad. And report plot means in the display panel, the graph of the drag versus cylinders number with iteration will be plotted. And if you click print to console, The value of the drag will be printed here in the console panel. Now if we click per zone, the drag of all these 4 cylinders will be plotted separately. Now click OK. In a similar manner, we will do for lift values. Select cylinder number 6, 7, 10, 11. Write the file name as lift and the lift direction will be Y positive. Create file, print to console and report plot. Put per zone. So per zone means all the cylinders lift values will be plotted separately in a same window. Now close this and now go to initialization. Usually we will do initialization from inlet. What we do in initialization, we will assign the primary variables values at t is equal to 0, means at the start of the flow simulation. So at everywhere the cell velocity value will be 1 and pressure values will be assigned by software. Now go to the calculation activities and go to the edit. We want to save our data at every suppose 50 time step. We also want to save case files with the data files. There are two types of file in Fluent. Case file. In case file, these values are stored. Which model you have used, what are the type of the solver, boundary condition, fluid properties, methods, monitoring. All these things are saved in case file. In the data files, the various quantities like pressure, velocity, vorticity, etc. are stored. So save these files in the folder where your in the working directory is. By any name you can save it. For example, you can put the name as RE100 and click OK. And append the file name with flow time. So every file will have the flow time with RE100 file name. Now click, and you can also click here to retain the number of files you want in case hundreds of numbers of files are generated. And if you put here 10, the only the latest 10 file will be kept and rest of them will be deleted from the system. Now put OK. One thing we forget, we should go into the monitor and click on the residuals. So residuals basically monitor the errors. So in any simulation, the error should drop with iteration, and until we reach a specified value of error, which is normally 10 to the power minus 6, we will consider the flow simulations to be converged. So once we will reach these errors in continuity, velocity, y and x velocity equations, these levels will be achieved, then the software will start new iterations. Now click OK. Now the last thing is run calculations. In run calculations, the time step size is 0.05 second. Let us, and it depends upon the how much you want to resolve your simulation in time. And let us put here 10,000 number of time step. So 10,000 time step, and every time step is 0.05 second. So in 10,000 time step we will go 500 seconds. So maximum iteration per time step will be 20, which is a default value. So if the solution is not converged, so the maximum iteration in one go will be 20, and the software will start next iteration cycle. And in one time step we will move 0.05 second as we have set here. and in a single time step there will be maximum 20 iteration. Now click on calculate. So you have to create a new file, yes, and now you can see that the residuals means errors are dropping. If the errors are not dropping, then there is something not good with your simulation setup. So you have to look at again boundary conditions, the methods you have choose to solve fluid flow, and also the drags will be plotted and lifts will be plotted. So the white line denotes the errors in continuity equation, and the red line denotes the errors in x velocity, and the green line in errors in y velocity. So these values are dropping, and after every cycle we proceed to the one time step, and here that is set up as a 0.05 second. So you can stop anytime, and you can see the drag values and lift values are changing, and the solution is still at zero point 0.3 second. So it will run about 50 second or 100 second until the simulation is stabilized. So let us keep it calculating, and in the next section we will tell you about the post processing and how to obtain the data and visualize data and analyze the simulation results.